after 3 introductory videos about Chapter 9, air standard cycles, finally we can get to the point of seeing how to uh, develop a thermodynamic model for a spark ignition engine and evaluate its thermal efficiency performance. So the thermodynamic name for a spark ignition cycle model is the Otto cycle, named in honor of the individual who proposed this cycle. So we're in Chapter 9. We're talking about air standard cycles. So remember, our working fluid, our substance is air that we're going to treat as an ideal gas. And remember, I've thrown a monkey wrench in the thing to give you an idea. A confusing part of the textbook and analysis is sometimes we're asked to do a cold air standard analysis, and other times we're asked to do what we call an air standard analysis. And they are computationally different. So let's get started and see what's behind the model for the spark ignition engine. So a number of folks who are better versed in engines than I am will know the difference between a diesel engine and a spark ignition or Otto cycle engine. So a little crash course on that. And then what I'm going to want to do is take an example problem, a very generic example problem that would be very similar, I hope, the type of problems you're going to be assigned to do, and show you how to go through the air standard analysis, or similarly, the cold air standard analysis for the exact same problem, and hope that you may want to refer to this video as you're working through your homework assignments. So what's the difference between a diesel cycle and an Otto cycle, or in other words, a gasoline engine? These two engines look similar, at least they do to me, don't they? Now, because and how are they similar? Well, they both involve pistons and cylinders. Now, sharper people than I will say, well, I see this is an inline piston and cylinder engine, and this is would be like a V8, a V-shaped engine. So certainly that is a mechanical difference. But the other key difference is that this is an image of a diesel engine, and this is an image of a gasoline or a spark ignition engine. So they look similar, don't they? So the usual assignment in Chapter 9, the usual assignment in Chapter 9 for either of these types of engines is to determine the cycle thermal efficiency for some given information related to the engine, and also determine the mean effective pressure that we defined. And I'm going to openly admit that I don't have this memorized. The mean effective pressure is the net work for one single cycle divided by the displacement volume. In other words, V max minus V min. And let's see, the cycle thermal efficiency, I've got that one. That's the energy sought over the energy that costs. So that's going to be W net, the net work for one cycle, divided by the heat added for one cycle. And of course, if you divide both of these by M, you get little W net divided by little QH. So this is the common assignment. This is the common analysis assignment in thermo for these internal combustion engines. But the devil is in the details. So you say, oh, that looks easy. Well, not quite so easy, because the computational devil is in the details for pulling this off. So I'm going to try to give you some hints on how do you start, what would you do? Some highlights of our thermodynamic model for the Otto cycle. In other words, the spark ignition engine cycle. I've blurred out the diesel cycle because we're not going to talk about that right now. But what kind of fuel do we have for our Otto cycle? Gasoline. Gasoline is our fuel. Kind of like we would model that, I think, as octane. Okay. Is a spark plug involved on the Otto cycle and the spark ignition cycle? Yes. Spark ignition. Yes, we've got a spark plug involved. How will we model? So this is a key to recognize for our thermodynamic model. How will we model the speed with which combustion takes place within the piston and cylinder? And the answer is we're going to model it as instantaneous. When the spark fires off, so we've got a mixture of fuel and air in our model, a spark fires off and kaboom, you get instantaneous combustion. And so remember, we're going to model that as heat addition. We're not going to get into the combustion physics here. We're going to model that as heat addition. And so we're going to model instantaneous combustion speed as a constant volume process. In other words, when the piston is at top dead center, where the pressure is the highest in the piston and cylinder, and the spark lights off, boom, you get instant heat addition. So in other words, heat is added at constant volume. In other words, heat is in our thermodynamic model of the spark ignition engine. All of the heat addition takes place when the piston is not moving. It is at top dead center. And that's going to give you in the model, it's going to give you a very large pressure. And that's what's going to give you the power stroke. So these are screenshots right out of your book. And so as a reminder, the physical sketch, we've got a closed system model in my dashed line. Here's where our ideal gas air is. We've got a spark plug. We know where top dead center is. We know where bottom dead center is. And the next thing we do is for this closed system, we're going to draw a pressure volume diagram. You must do this every time you're assigned a homework problem. Do not start your computational work without drawing the sketch of the cycle. That is a must. So here's what our PV diagram looks like for our Otto cycle model. So let's spend some time looking at this. Let's see. So process 1 to 2, that would be the isentropic compression process, going from bottom dead center, state 1, maximum volume, compressing. So the piston is moving up in the cylinder, okay, a compression process to state 2, reversible adiabatic. What's the work going to be from 1 to 2? Can you visualize it? It's less than 0. You're going to have to figure out what that is, but work from 1 to 2 is less than 0. Okay. State 2, we're at top dead center. Okay. We should be able to figure this out in our engineering heads without being given the sketch. Process 2 to 3, well, that's where the spark hits, and our model is heat addition that's instantaneous. So we don't even have time for the piston to start moving. Our heat addition goes from 2 to 3. Look what happens. Constant volume heating, and the pressure is zooming up dramatically to P3, a very high pressure within the piston and cylinder. Okay, so the heat addition is over. So now we've got our power stroke model. Power stroke model. Reversible and adiabatic, 3 to 4. Wow, is the work out from 3 to 4 going to be positive or negative? Definitely positive. I can see it with my eyes. That's why it's so important to draw this pressure volume diagram on your paper. Isentropic process, 3 to 4. Okay. And then finally, the heat rejection process. We've got to finish our thermodynamic cycle. So somehow we've got to get back to state 1. And our model is that we're going to reject heat from 4 to 1 at constant volume. So that is different than the mechanical cycle. That's a different model altogether than the mechanical cycle drawing. So just be aware of that. Now, it turns out that we're not even going to have to mess with this, with the heat rejection in our analysis, and do you see that the work from 4 to 1 is 0? So for our Otto cycle model, let's recap a little bit. What's the work from 2 to 3? I didn't mention that. Area under the curve, integral PDV. Well, it's 0. No work is involved from the heat addition process. Heat rejection process, 4 to 1. No work is involved. So for this thermodynamic model, there's only 2 places where work is involved. 1 to 2, isentropic compression, and 3 to 4, isentropic expansion. And then finally, recognize that R, the compression ratio, is simply V1, the maximum volume, divided by V2. Okay, that's critical. So I wanted to spend some significant time on this slide trying to get you to see how the physical sketch matches up with the PV diagram. And I do want to make the important point that you must draw a pressure volume diagram on your work, whether it's a homework problem or a quiz or a test. Do not leave that important part out of your showing your solution. Now I'm going back to this cold air standard and air standard business as a reminder. So in your problems, you're going to be instructed to either use a cold air standard or an air standard, one or the other, and you're going to, I ask you to work with your instructor in class to get some specific guidance on how to do this. Okay, now I'd like to propose an example problem that I see as representative of your homework problems for internal combustion engines in this Chapter 9. So I'll read the problem. An air standard Otto cycle operates with a mass of 0.65 kilograms. Okay, mass is given in a piston and cylinder. At the beginning of the compression process, the pressure is 100 kPa and the temperature is 290 K. Okay, so that's given, pressure and temperature at the beginning of the compression process. It says the compression ratio is 8. That's the Vmax over Vmin is 8. It says the maximum temperature in the cycle is 2200 degrees K. That's going to be the maximum temperature after heat is added. Determine the following. This is a common assignment. The displacement volume. What does that mean? Displacement volume. That's Vmax minus Vmin. The heat added. That's going to be the number of kilojoules where we're modeling the combustion process. The thermal efficiency, what's that? Energy sought over the energy that costs. Well, for one cycle, we will determine the net work in kilojoules divided by the energy that costs, the heat added in kilojoules. That's thermal efficiency. And then finally, the mean effective pressure. I can't remember what the mean effective, it has something to do with W net and has something to do with the displacement volume. I can't remember it, so I'm going to have to refer back to the definition to calculate the mean effective pressure. Okay, so what I'm going to do is I'm going to try to show you how to work through this problem using either the air standard cycle, that's what the assignment is, or the cold air standard, which was not assigned, but I want to give you some type of document or video to show you how you would work through either assignment. Okay, well, let's start with a sketch. Okay, we've got a closed system. I'm going to draw down my pressure volume diagram. There it is. I've drawn pressure volume diagram for the Otto cycle. Okay, I'm going to write down the ideal gas equation of state, PV equals MRT, because I've got M and I've got, I think I've got P and T at state 1. Okay. I'm going to plan my work, process 1 to 2, heat in is 0, work out, it's going to be a negative number. Process 2 to 3, that's the heat addition process. Well, that's going to be QH. I'm going to need to find that, right? W out, well, that's 0, no area under the curve. Process 3 to 4, the expansion process, that's like the power stroke model. There's no heat transfer involved in that, reversible and adiabatic. Work out in kilojoules, yes, positive. And then 4 to 1, that's QL, and there's no work involved there. And so I see in my planning, if I can get QH, I've got the denominator, and if I add up all my workouts, I get W net, and I've got the thermal efficiency, and I'm home free. So I only need work out for 2 processes, and I only need QH. So I'm not going to do anything more than I have to do. Okay, there's my plan. Okay, so let's see. Now I'm going to start my solution. All right, and so I'm going to start with a sketch in a green text box. I must plop down my Otto cycle model on the PV diagram. And I study, what am I given? What am I given? And I do recognize that I'm given pressure and temperature at state 1. So by process of elimination, I'm going to start at state 1. Okay, start here. And then I know the ideal gas equation of state. I might as well, can I calculate V1? Yes, I'm given P1, I'm given M, I've got R. R is 0.287 kilojoules per kilogram degree K. Know that off the top of my head for air. And T1 is given. So I can calculate capital V1. It's MRT1 over P1. And also I'll go ahead and calculate little V1. It's simply going to be RT1 over P1. Either of those will work. Okay. But I need V1 to get the displacement volume, don't I? So I need V2. That's Vmax. I need V2. Okay, let's see. I need V2. Well, let's see. What am I given? Let's see. I need to determine the displacement volume. Here's what I've got to find. Okay. I was given in the problem statement that the compression ratio was given. It was 8. And so V2 over, so remember that the compression ratio is the big Vmax over Vmin. So V2 is simply V1 over R. Easy. So it's 1/8. V2 is 1/8 of V1. And I'm going to go ahead and calculate little V2 is little V1 over R. So I've got a 25 on my quiz. Okay. I've got the displacement volume. Check. Now, what's the next thing I do? The next thing I need to do is I've got to figure out state 2. I'm going to have to figure out what T2 is to keep moving along. I'm thinking ahead. I'm going to have to use the first law for process 2 to 3 to get the heat added. So, I'm also going to need the work from 1 to 2, right? So I'm going to have to get T2 in order to find the work from 1 to 2. I'm going to use the first law for 1 to 2. Let's see, what's the heat added from 1 to 2? That's 0. So if I can get T2 and no T1, I can use the first law for process 1 to 2 to determine the work from 1 to 2, since Q is 0 from 1 to 2. Does everybody see that? Okay, and so I need delta U. I need delta U from 1 to 2. And so therefore I've got T1, so I need T2 in order to determine U2. So for an air standard, for this problem where it said air standard, I've got to go to A22. And let's see, I've got a study on what I have. I've got V2 over V1 is equal to 1 over R, so that's given. I can look up VR1 in table A22 because I've got T1. Okay. So let's see, V2 over V1 is known. I've just looked up VR1, so I can solve for VR2. Okay, so I've got a number for VR2. Well, I study on table A22 and I see, well, if I've got a value for VR2, I can go back and I can interpolate back for T2 as well as U2. So I can do that twice. So I can solve for T2 and also solve for U2. Now, our assignment is not cold air standard, but if we were assigned cold air standard, the way you would do this is to recognize that P1 V1 to the K equals P2 V2 to the K, and you'd solve for T2 in that manner. But let's just stick with air standard right now, okay? You can use this perhaps as a help if you're assigned to do this problem with the cold air standard. Okay, so now we've got our sketch, okay? We're looking for the work from 1 to 2, okay? Well, how do we do that? Let's use the first law. For process 1 to 2, it's an isentropic process. It's reversible adiabatic. So I'm going to see Q in minus work out is U2 minus U1. Wow, okay. That goes away. And so, wow. And so the work from 1 to 2 is simply U1 minus U2. And I hope that I've convinced you that you can solve using A22 for both T2 and U2. Okay, so check. I've just determined the work out from 1 to 2, and it's going to be a negative number. Okay, at least I'm plugging along. If I had cold air standard, do you see that you would evaluate U1 minus U2 as C sub V, which would be a constant number, times T1 minus T2, both of those you know now. All right, well, now we've got to find P2. We've got to find P2 because we're looking ahead, and we're given T3. We're given that in the problem statement. So somehow we've got to find T2. And so look, if I can if I can solve for P2, I'm going to be in good shape. Let's see. And so let's see. We just found T2, didn't we? In our previous work. We just found T2. And so I can solve for P2 using the ideal gas equation of state, no matter which model I have, cold air standard or air standard. P2 is simply P2, V2 is MRT2. And so I'm going to solve for P2. Well, let's see why. And so let's see. I know P2, V2, and T2, right? And so now I'm going to go and I'm going to try to figure out state 3. Okay, so let's look at state 3, okay, and let's see if we can figure out. We know that V3 equals V2 for the spark ignition model, the Otto cycle. So we can write down that V3 equals V2. T3 is given. Okay, so we can solve for P3. P3 V3 equals MRT3. Wow, okay. And so I've got V3 is V2, M I have, R I have, and T3 is given. So we'll solve for P3. Okay, great. So now we've got P3. That enables us to write the first law for process 2 to 3. Oh, okay. I was just thinking back. Why did I need T2? Well, I'm going to write the first law for process 2 to 3. We're going to determine the heat added. So now we're going to write the first law, process 2 to 3. Let's see. Q from 2 to 3 minus W from 2 to 3. Oh, that's 0. No work equals U3 minus U2. We're looking for the heat. We're looking for that. Wow. And so let's see. For air standard, we have T3. We solved for T2. Yes, okay. So we can look up U3 and U2 and immediately solve for the heat added. QH, Q to 3, is U3 minus U2. So we're going to look up, we will have looked up U3 and U2 in table A22. We're well on our way. Now we've got to analyze process 3 to 4 because we're looking for the work. We're looking for the work for process 3 to 4. How are we going to do that? The easiest way is to look at the first law for process 3 to 4 because we know the process is reversible and adiabatic. Q from 3 to 4 is 0. And so let's see. We can find T4 either way, whether we have cold air standard or air standard. Let's look at our air standard approach. So we need T4, and we need T4 in order to get U4 for our first law, because we've already found U3. All right, so let's see. We've got V4 over V3. Little v4 over little v3 is R. Look at that. So that's the compression ratio. Well, we can look up VR3 in table A22 because we have T3. It's given. So we're going to write down a number for VR3. Well, we've got V4 over V3. That's R. We'll solve for VR4 in table A22, and then we will interpolate back for both T4 and U4. Okay. And why are we going to find U4? We're going to put that in the first law to solve for the work for process 3 to 4. Okay, so process 3 to 4, Qn 0 minus W from 3 to 4 is simply U4 minus U3, or in other words, the work from 3 to 4 is U3 minus U4. Wow. And so U1 is already in it. We've already looked up. So we will look up U4 in table A22 and solve for the work from 3 to 4 using our air standard model. If we're over here on cold air standard, you see that U3 minus U4 is simply CV, a number, times T3 minus T4. We're just about there. We're just about to the promised land. The net work, it's the work from 1 to 2. We've already found it. It's a negative number. The work from 2 to 3, it's 0. 3 to 4, we just found it, a positive number. 4 to 1, 0. Okay, and so the capital W net is the mass times little w net, right? So we've got the net work. Let's see, the QH was Q from 2 to 3, and so the thermal efficiency is little w net over little QH, or capital W net over capital QH. We have all those numbers, so now it's a calculator effort to get the thermal efficiency. Let's see, mean effective pressure, that's little w net divided by little v1 minus little v2. Okay, we've gotten all of that information, so that's going to be just plug and chug to get the mean effective pressure in kPa. You say, whew, that is a lot. Wow. So that was a lot of work. I'd sort of drug you through that pretty quickly. Okay. If you'd like to see a video of the detailed numbers worked out, if you go to my homework solutions playlist, I'm going to show you step by step by step how to do problem 9.1 in the textbook using the air standard model that I tried to show you here. I work it out exactly the same with the cold air standard model. And then similarly, if that's not enough for you, if you go to my example problems for air standard cycles, I've got yet another homework problem that I worked out called Otto Calc. So that is a different problem than 9.1. And I may work it out both ways and compare. So I go through the nitty gritty numerical values for that basic analysis. So, whew, that was involved, but I'm trying to show you how would you go through step by step. Rather than using formulas, you're going to find that you're going to benefit by understanding the step-by-step analysis instead of using formulas. So Otto cycle, it's a closed system analysis. Remember, it involves isentropic compression and expansion processes. The heat addition model is instantaneous or constant volume heating that models the spark ignition process. And only 2 of the processes involved work. So I may be able to read your mind and think, why is this guy telling me all these step-by-step things when the book gives me these really cool formulas to plug in for the Otto cycle? Why is he torturing us like this? What I want you to be aware of is that in quiz and test situations, it is very common for instructors to ask you to do an analysis of a part of an Otto cycle. Might say perhaps analyze only the isentropic expansion process given a couple of pieces of information. Do you see that if you get that on a quiz or a test, you will be sunk in terms of your understanding if all you're doing is plugging and chugging through formulas that you're copying and pasting out of the book? for a full analysis. So the reason I drag you through these step by step by step computations is to try to get you prepared to perform well on your quizzes and your tests when the instructor gives you just a little part of a cycle to analyze. And I think you do see, I hope you see, that you'd be dead in the water if you didn't understand how to analyze each little process. So that's a little bit of a word to the wise. I hope it helps you in your performance, but even more importantly, I hope it helps you prepare for engineering practice. Once you get out into the field, you're not going to be simply plugging and chugging into formulas provided by a textbook.